In this video, I'm going to talk about the motion graphs of waves. Please take a moment to read the success criteria for this video. As with all graphs, it's really important that you read the axes to know exactly what's being graphed. In this case, I have displacement on the y-axis and time on the x. So what is this really trying to tell me? Well, if I have my little rubber ducky here on the wave, what this is giving me is the graph of this duck going up and down here at the exact same spot. It's not moving forward or backwards, and we know from before that it's going to go up, slow down, stop, turn around, speed up, slow down, stop, turn around. And that's what we have here in our distance-time graph. As with all of our distance-time graphs, we know that the gradient of this graph is going to give us our velocity. And so that's also really important for us to think about. If I take and I measure the distance from here to here, or here to here, or here to here, you get the point. What have I measured in all of those places? Now, the misconception, and people usually just jump to and say, wavelength, that's one complete wavelength. But the problem is, remember, this is time on my x-axis. So what have I actually measured here and shown you is the period. These kind of details are going to become really important in some of the questions we're going to solve. In my next graph here, I have a distance displacement graph. So notice I have its displacement here on the y and its distance on the x. So I guess I really should have labeled this displacement distance graph. Anyway, if I take and look at this, what is it trying to tell me? Well, I'm looking at a wave from the side and I've taken a snapshot. So this is at one instance of time. So if I mark like I did on the last graph, from here to here, or here to here, you get the point, any 2 points in phase. What do I have this time? It's a distance, so now it's going to give me the wavelength. I can still get my amplitude, just like the last one, from here to here. So let's go ahead and try and use this information and use these different types of graphs. So the labels on the graphs are intended to show the wavelength and the period and the amplitude of the wave, but only one of them is correct. Which one is it? Remember, always start by reading the axes. In A, I have a displacement-distance graph, and it's measuring period from here to here. That is a measurement in time, so this one is definitely wrong. Let's go to the next one. In B, all I'm doing is checking first wavelength and distance. That's a possibility. But now I have amplitude going from the peak all the way down to the trough. No. The amplitude is from the equilibrium line to its maximum. Let's try the next one. I have lambda and time. Again, they don't match. So let's just double check this last one. I have in the x direction, I'm looking for period, and that's time. Yes. And my amplitude goes from the equilibrium line to the peak. Yes. Now note, I could also go from the equilibrium line down to the trough. This one is correct. Okay, so let's do some actual problems here. A longitudinal wave travels through the medium from left to right. So here's my wave moving in this direction. Let's take a look at my axes. It says displacement time graph. So that means from here to here, it's going to be my period. Question A, calculate the magnitude of the maximum acceleration. On a distance time graph, my gradient gives me velocity, but not acceleration. Here's where we have to remember that the particle is actually undergoing simple harmonic motion. From my data booklet, and oh, I love my data booklet, We know that A equals negative omega squared x, and omega squared is going to be 2 pi over the period, and that I have here. So I'm going to read my graph, and remember, I'm going to have to read to the nearest half square. In this case, where will I get my maximum acceleration? I'm going to get my maximum acceleration at my maximum x value. So if I look here on the axes, that will give me an x value of 6. And looking closely at my graph, my period is going to be 2. If I put that all in, so negative because when my x is a maximum in the positive direction, like it is here, then that means my acceleration is actually going to be towards the equilibrium. Likewise, if it's down here and I have a negative x, my acceleration is towards the equilibrium, and that means in a positive direction. If I put all these numbers in my calculator, pick it up, and here I go, I get 14.8 meters per second squared. I'm going to put this up at the top so I can erase it and go on to the next question. Okay, part B. Calculated speed at 6 seconds. So let's move along the time to 6 seconds. That's going to be down here.
Now that's when my x is at a maximum.
And on my distance time graph, if I want the speed, I want the gradient. And right here, my gradient will be 0. So my speed at 6 seconds is 0. It stopped. State its direction of motion at 3 seconds. So let's look at our graph. At 3 seconds, it's right here. So we're starting at the equilibrium. And which direction it's going? Well, it's actually going to start moving in the positive direction. Now here, stop for a second. This is really important. What we have here is a longitudinal wave. And if it's traveling from left to right, let's assume that right is positive. Okay, so in this case, this wave is not moving up and down. So it would be incorrect to say that my wave right now is moving upwards. My wave or my particle at this exact point here is about to move to the right. One other note of warning about these kind of questions is you should really refer to the page. For example, if my page is laying flat on the table and I say up, it actually could mean out of the table or into the air, or it could mean to the top of my page. So in this case, to the right, I'm using that terminology because of what it said here. All right, last bit here. Calculate the speed at y equals 0. Now notice it says speed, not velocity, so I don't have to worry if it's going in a positive or negative direction. And it does mean that I could actually take this one, or this one, or this one, and at this point it should be all the same speed. Remember what's happening with a particle in simple harmonic motion. It is stopped at the edge. It speeds up, slows down, and stops. So this is actually the position of a maximum velocity or maximum speed. Okay, so we're back to simple harmonic motion. I'm going to go to my data booklet and look for an equation we can use. Found it. I can use this equation to find the speed of something traveling in simple harmonic motion if I know its angular frequency. X naught is the maximum displacement, so the amplitude, and
X is the displacement at the given point.
So at y equals 0, my value here is going to be 0 as well.
Let's substitute those values.
Okay, so my omega was 2 pi over the period, and my period was 4, times my maximum x, which is 6, gives me a speed of 3.85 when it's crossing y equals 0. Okay, one more problem. A transverse wave is traveling in a medium from left to right. The graph shows the variation of distance x with the displacement y of the particles in the medium. One of the particles in the medium is labeled with P. If the period of the wave is 5 seconds, calculate the speed of the wave. So my equation is V equals F lambda. I know my frequency. Oh, no, I don't. They gave me the period. No problem. I have frequency is 1 over the period times my wavelength. Am I going to get my wavelength from this graph? Yes, because I have distance on my x-axis now. If I take a look, I can see that one wavelength, just to double check, 2 wavelengths. It's always better to do multiple wavelengths, take the distance and divide by how many wavelengths you have there. In this case, I've chosen perfect numbers for my graph. Don't assume the IB will always do that. In my case, I have my period is 5 seconds and my wavelength is going to be 2 meters. And that's going to give me 0.4 meters per second. Double check. You know the units are going to work out, right? I've got meters on the top, seconds on the bottom. Okay, draw on the graph where the wave will be after 2.5 seconds. Remember, this is a snapshot, and since the wave is moving to the right, I would expect my peak that is here now is going to move this way. But the question is, how much farther? Now, you might be tempted just to go and draw any kind of wave in here just a little farther, but they give you a very specific time into the future, so that's not going to work. Well, we know that the period is 5 seconds, so in this case,
2.5.
that means my wave would have moved along 1/2 a wavelength. So what used to be here will now be here. What used to be here is now going to be here. Let me draw it in. Now this really should look like a sine curve, and you need to do your best. So for example, in this case, perhaps I'm a little too pointed here, and I might want to fix that if I was on the real exam. I should not see any points. Okay, so this part here at the top and the bottom, the crests and peaks are rounded edges, please. Do not draw this as a zigzag of straight lines. You will not get full marks for something like that. Part C, calculate the angular velocity of the particles. Okay, so angular velocity, that's our omega, 2 pi over t, 2 pi over 5, and my calculator gives me 1.3. I'm going to round it to 2 significant figures. So really, up here, I really should have 4.0. All right, what are the units of angular velocity? They're actually radians per second. Calculate the speed of the particle p at the location marked on the graph. So let's go back to that data booklet and our equation. So my omega was 1.3 times the square root of x naught, in this case, is going to be 4.5, minus my position of x. Now remember, we're supposed to read this to the nearest half square. So this right here, I'm going to say that it is in the middle of these two pieces here. So that would be 2.75. I'm going to pick up my calculator and put this all in, and I get 4.6 meters per second. Okay, so at what direction is particle P moving? Now, here it is right here. Remember, my blue line is where it would be later in time. So it's going to have to go from here down to here for my next line. A common mistake students make, for example, if I chose this point here at the peak, is to say that this point is going to be moving from here to here. Well, remember, the particles actually aren't moving. All they're doing is going up and down. Okay, so the wave will travel in this direction, but the particles don't. So from here and And a little bit time later, it's actually moved down to here. So in what direction is particle P moving? It's actually moving in the negative direction. That's a better way to say it than to say it's moving down. Or you could say to the bottom of the page. And the last part of this says, compare the motion of the wave and the motion of the particle P. So the wave is moving to the right, and it's going to be moving at a constant speed. Okay, so tell us more than just direction. Whereas particle P is going to be moving downwards, or better yet, in the negative direction. But we also know that P is going to undergo simple harmonic motion. That means it's going to have acceleration. It is not at a constant speed. So I hope that's helped you. Please take and read the success criteria one more time. Please go back and look at the graphs. Always remember to check the axes before you start any question.